So, with that, let me introduce William O'Mullane and welcome him back to Cork. You were born in Cork, weren't you? I know you said you grew up just across the river from here. William attended UCC here, graduating in '93 with a computer science degree. Went on to the University of Barcelona, where he got his PhD in physics. And he's been working on science projects on and off since 1996. Well, on, no off. When he joined the Hipparcos CDROMS for the European Space Agency. William actually worked in the European Space Agency, where we visited just outside Copenhagen some years back, if anybody here was on that trip. Great trip. From 2000 to 2005, he worked at the Space Telescope Science Institute in Johns Hopkins University. He tells me this is where they steer things like the Hubble and the James Webb telescope. Involved in the Sloan Digital Sky Survey. And in 2005, he rejoined ESA as a Gaia Science Operations Development Manager. On the 1st of April, and I hope that's not prophetic, 2017, he took on his role as project manager for the Vera Rubin Observatory data management. In this role, he leads a distributed team of over 100 professionals, and their role is to successfully deliver on the DM system, the data management system. This includes the stewardship of the Vera Rubin Observatory data management, technical and scientific vision, as well as the overall execution, quality and timeliness of all DM construction activities. Since 2018, as if all that wasn't enough, since 2018, he's also the Deputy Project Manager for Software. So, ladies and gentlemen, I'd like to give a very warm welcome to William.
All right, good evening, everyone. Hi. So last time I stood at a podium in UCC was in 1992, I think. Maybe 1993, possibly. So today I'm going to tell you a little bit about Vera Rubin Observatory, and I just want to get my speaker notes because they've disappeared somehow. Let me just get those from here. So, yeah. So Vera C Rubin Observatory, it's a new observatory being built in Chile. You may know the European Southern Observatory, that's a bit further north. Gemini is our neighbour, they're just on the next hill across from us. And we're built on Cerro Pachón. And our idea is to build a survey telescope. It will have a 10-year mission observing the southern sky pretty much constantly over 10 years. And all data products are just given out to the scientists. There's no observing proposals. People don't come and say, I want 2 hours of this or whatever it is. We just do what it is each night. So just to give a little, like, why do you build telescopes like this? I guess this is the Astronomy Club, so many of you understand that or know why we build telescopes. What always fascinated me was the origin of the Milky Way and where did our Milky Way come from? How did we get this set of stars and spiral arms? So this is a picture, it's an artist's picture of what our galaxy might look like. Because part of the problem is we're sitting in our sun, kind of in a spiral arm on the edge of our galaxy. And when we look out, we either look out at nothing in one direction, or we look out into the middle of our galaxy where there's lots of dust and stars and lots of things in the way, so we can't actually see very well. So it's a pretty mysterious thing, our galaxy, and has been for a very long time. But if you could actually measure the positions of the stars and their motions, you can use it like a little history map. If you know where stars are going, you can also figure out where they came from. And so you can work out all the motions of the stars. And this is an animation using actual data from Gaia, where someone has shown that a small galaxy was consumed by our galaxy, and the stars mixed together. But because of the motions of the stars, you see this group of stars still move in the same way, differently to the rest of the stars in the galaxy. So this has always been a theory of how galaxies are formed, but we never had data before that said, oh, yeah, no, I've actually found these hundreds of thousands of stars that all move in the same way, and they move differently to the rest of the galaxy. And so we're finding more and more of these galaxy mergers from something like Gaia data. And Gaia data was for sort of a billion stars, 1.2 billion stars. And I need to get to the next slide. Perfectly. 1.2 billion stars, and for Rubin, we'll go to 20 billion stars in the galaxy, and 20 billion galaxies outside our galaxy. Gaia doesn't see galaxies. So we'll extend this kind of idea of the motions and mergers of galaxies and where our galaxy came from, or archaeology of our galaxy, really quite a lot with this new telescope. This is just a picture with one of my cameras, not as nice as the ones you were just showing me. It's a single exposure. But it's the Magellan Clouds, which you can only see in the southern hemisphere. You don't see these up here anywhere. They're quite pretty. And that previous galaxy merger, they showed also looking at the chemical composition of those stars of that galaxy that was consumed by our galaxy. They're very similar to the Large Magellanic Cloud. So it could be that that's also a remnant of that galaxy merger. And these are the kind of theories that astronomers have had for a very long time, but there's been no data where you could say, I can prove or disprove this happened. And now we're beginning to have that kind of data. And we'll bring more and more of it. So other things that we will do with Rubin are look for all of those little things that are out in the out around Jupiter, all those asteroids, all those rocks, big ones and small ones. There's a couple of nice little things on here. Just we lived in Arizona for a long time. That's the Barringer crater, and these things in there are to scale. That's our observatory, the pyramids of Giza. This is from one meteorite hit in the Barringer crater. Tunguska, Shumaki Lever. These are all things that you've maybe read about or seen. They're all meteorite hits. Once we can map, so one of the things that we will be able to do is map about 90% of objects bigger than 140 meters around our solar system, which means we should be able to get orbits for most of them, which means we have it's still a 90% chance of predicting any of these events. Whether we can do something about it or not, that's a different question, but at least that's one of the goals. We'll start to map all of these things out. And then there's dark matter, dark energy. We have, again, lots of nice theories from astronomers and physicists about how the universe expanded. This is the typical Planck sort of diagram you've possibly seen from somebody else at some other point in time, but as you stare out with your telescope, you're actually looking backwards in time. So we're sitting in our solar system, and if we could look far enough back, we see light from all the way from the beginning of time if we could do that. Typically, this back here, we don't see light anymore. We start to look for cosmic microwave background. So you get missions that look at this very faint frequencies that are in the background. The galaxies are in there somewhere. So as we look further and further back at the 20 billion galaxies, we should be able to see some of these very, very historic events that happened billions and billions of years ago and see how they unfolded. And so this will start to help us to see how the system, how our galaxy system built and how all of the other galaxy systems were built and how they interacted with each other over a long period of time. The other thing is with all of these theories, there's like problems with it. They don't quite work unless you have this thing called dark matter or dark energy. And quite a lot of it is dark energy or dark matter. We really don't understand it. And it's true. People say, why do you call it dark energy? It's because nobody knows what it is. No one can really put their finger on it. Lots of theories. So it's just called dark. We can't see it. Pretty sure it's there. So again, with something like Vera Rubin, where we will have data from the entire southern hemisphere over a very long period of time, the entire sky, and quite accurate, we'll start to be able to have more data about how galaxies are sheared, how light bends around dark objects. So we should be able to give more information about this dark energy and dark matter by looking how it interacts with the light coming from the very distant galaxies. And we don't have very good large data sets for doing this at the moment. We have little data sets. So you get lots of interesting papers about individual things, but we'll be able to do this with a much bigger scale, much more statistically. So the final thing is the variable sky. We have a very large field of view on this telescope, so we're going to see everything in the sky every 3 nights, more or less. Every exposure is 9 square degrees. It's very, very large. We're going to template the sky. We're going to look at the pictures we take. We're going to subtract them from the template. That's what this little diagram is. And for every one of those, every 30 or 40 seconds, we're going to say, oh, all these things changed. Now, it could just be it's a star that's got brighter, a variable star, a very normal thing. But it could be lots of interesting things. So there, this kind of supernova, exploding stars, all of those type of things which happen, that if you don't catch them at the right time, you can't really see them happening. Some of them last a few days, some of them last a few minutes. So being able to tell someone within a minute, oh, something happened over here, you can point another telescope at it and maybe you'll observe it for a few days and you'll be able to find out more information about some of these supernovae and other interesting things. So yeah, this has a list of things. I'm not going to read through them. You can get the slide deck afterwards, but the main ones are usually exploding stars. That's what most people are interested in because we use this for getting distance scales for how far away everything is in the universe. So that's our survey. It's the southern sky. We're going to pan over the entire sky, as I said, we covered the whole sky in about 3 nights. So we revisit every part of the sky every 3 nights, 3 or 4 nights. We'll go quite deep, so 27th magnitude, it's quite faint. I'll explain a little bit more exactly what that means in a second. And we spend 90% of our time on this survey. There's 10% for other things. If someone says there's a gravitational wave event, we might point our telescope at that. It's interesting that we would do that. At the moment, when people like LIGO say there's a black hole merger, the accuracy of that is around 9 or 10 square degrees. And our field of view happens to be 9 or 10 square degrees. So it's one of the few telescopes that could quickly find something like a gravitational event that's triggered by LIGO. So it's one of the things that we would do where we would pull out of the survey and go, okay, we'll go look at what they're doing for that. So about the data, which is what I do. Each of those images, every night we're taking images, about 20 terabytes of them. It adds up to about 50 petabytes over the 10 years, or about 5 petabytes a year. By the time we've processed all of that, because astronomers call it data reduction, but what they mean is data explosion. They take a bit of raw data and it ends up being 3 times bigger, so we'll probably about 100 petabytes by the time we're finished. The catalogue alone will be 15 petabytes when we're done at the end of this mission. So we've built a special database just to deal with the catalogue. And again, the survey map over here is a simulation. There's a lot of scientists discussing, I want to see this, and I'd like hundreds of observations of that. And a group gets together and decides, well, this is how we're going to satisfy everyone's needs. This is what we're going to do. So if you look at this little map up here, you see that it's green mostly, that's about 800 observations. So for every point on the sky in 10 years, we'll have about 800 pictures or images. There's 6 wavelengths, so it's not 800 of the same wavelength, but you have 800 images. And the purple ones are a little bit less. I mentioned earlier, we're in this dusty galaxy. If we look into that dust with this camera, we're not going to see that much. So we want to do that, but there's no point in taking hundreds and hundreds of images because we're not going to see more, we're just going to see more dust. So those purple bits are a little bit less. And then you see a couple of yellow bits, and those are 1,200 observations. So there are what we call our deep drilling fields. We're going to really look at those very frequently. We're going to come back to them more often so we can see very, very deep. And we'll stack those images up. It'll be quite big. So a big field of view, as I said, it's 3.5 degrees across, 9 square degrees. That requires a large mirror. It's 8.4 meters. So there's myself and a couple of my team standing at one side of the surrogate mirror. That's a piece of metal that we use for testing the telescope. It's the same weight, same shape, has similar characteristics to glass, even though it's a piece of metal, so we use it for testing. And that's the real mirror. It's the real piece of glass. It's uncoated. And the blue is just a protective optical layer over the glass, so it gets torn off and cleaned before we put the coating on. So it's pretty good, 16,000 kilos, 16 tons of glass. It's actually not all glass, it's honeycomb. It's an interesting silicon carbide structure, and then there's just 3 centimeters of glass laid on top of it. So it's actually quite flexible and reasonably light considering this, the size of it. So that thing gets lifted up. For me, at least, like one of the things I find fascinating about observatories and space is the same. Like you see this thing is like, this is a piece of engineering, you see science equipment. And for every piece of science equipment, there seems to be 100 other things, especially just for moving it or picking it up or manipulating it in some way. So this whole device is a big white pentagon with suction cups on it. Because you think, how do you move a mirror? You can't pick it up by the edges, it breaks, so you have to put suction cups on it. I find it fascinating. So it's picked up, it's moved. It was polished in Arizona, baked in Arizona under the football stadium, which I find quite strange, very American. So under the football stadium, we picked it up, we put it on a truck. So I was lucky enough to be in Arizona when that was happening, so I took most of these pictures. Truck drives out the road, you get a police escort, quite nice. It gets put on a ship, that's not me. It gets shipped off, BBC Manitoba was the ship that we had. It sails down through, so the road trip from Tucson is actually to Houston, and then in the port of Houston it's put on that ship. That sails down through the Panama Canal and comes out and down to Chile. I asked them why they go all the way over there, not to the port of LA, but LA apparently is a very congested port, plus you have to go over a mountain, and they don't like taking big heavy mirrors over mountains, they'd rather go to Houston, it's a flatter road. So it's hauled off the ship, and then you go through some very narrow spaces. So when you go up to the mountain in Chile, there's this tunnel that was dug for the Gemini mirror, which is 8 meters, ours is 8.4 meters. It still fits, the tunnel is big enough. But there was people walking on both sides. Truck is going very, very slowly, and those guys are going, yep, it's okay, it's okay. And then you get out onto this is the road up to the observatory. This is near the top. It's about, in a normal car traveling at 40 kilometers an hour, it's an hour's drive. With those trucks, they go about 20 kilometers or 10 kilometers an hour. It takes them a long time, 4 hours to get up to the top. So you can actually see on the top of that picture, that's our observatory under construction. That one is Gemini, and that's SOAR on the other end. So we're all laid out on top of the mountaintop. And you'll notice there are 2 trucks, because one truck is not enough. Doesn't have enough traction to pull the 16 tons of glass plus the box that it's in weighs 40 tons. So it's quite a heavy, and it's bulletproof. Apparently they were afraid some Texans might shoot at it. It could happen. So eventually it gets up on the summit. It was parked in a shed basically. It sat there for a few years. And then we got the 2 trucks back up. And we hauled it out of the shed and we brought it over to the observatory, which is now finished. And again, this corner took 4 goes. We just wouldn't make it around the corner, couldn't get the thing up there, had to get a road scraper in to move it, just to get around the corner to get into the observatory. So you come all this way, thousands of kilometers, and then you get stuck on the last corner going into the observatory. But it got it in there in the same day, finally. They were all very happy, all the engineers. And then we coated it a few days after that. So we took that piece of glass, it went into the coating chamber on the 3rd floor of the observatory, and that's the shiniest thing you're ever going to see, I think. It's pretty good. In the interest of time, I'm not going to play it. There's a very, very nice video. It's linked on that, and you could watch it, or you can search for it. You'll find it. If you want to watch the video of the coating, it's very, I like it. It's pretty amazing. But I will not go over that. So we also have a camera. if we're going to do this very fast survey, we need a very fast camera. So we have this 3.2 gigapixel camera. That in itself weighs 3 tons. It's the size of a little minivan. The person here is for scale. So you can see the camera is about 1.4 meters in diameter. It's about 3 meters long, 4 meters long. And as I said, each exposure, it's a big picture. It's 8 gigabytes. So each image that we take, and we don't even think of it as one image, we treat it as hundreds of small images because each CCD we take as a single image, but basically together they're about 8 gigabytes. So it's pretty good. And if you want to, like, it's very hard to comprehend how big this camera is. So your normal digital cameras that you have, these days we all have a 4K sensor, your iPhone, whatever, they're a 4K sensor. But this is not just a 4K sensor, it's a square 4K sensor. We have 196 of them. And so if you think about your 4K TV, you need 2 of those 4K TVs just to look at one CCD. So you need 390 or 378 4K TVs if you want to look at every pixel that's coming off that camera. If you want a pixel to pixel on your TV. It's a lot of TVs, or iPhones, or whatever you want to consider. And you need 2 because normally you're in landscape mode and you don't have the second half. We're square, so you need 2 TVs to see one image, one CCD. So that camera is all done. That was the very happy camera team. When they're finished testing, we're done. They did a little ta-da, and it's been shipped and it's sitting up on the observatory. So it's the last big piece of equipment that we've been waiting for to get the observatory going. And it just arrived the last couple of days. I think Ryan Powell says there's going to be a press release tomorrow. The biggest camera in the world. It did get a Guinness World Book of Records entry last year as the biggest digital camera in the world. And it got a second Guinness record for the biggest lens, because you think about that. It's a big camera, you have a lens on the front of it. The lens is funny actually, because we don't always have lenses on astronomy cameras. But this is so big, it's hot. It's hot, you have to cool it. If you cool it, you have to put it inside a chamber, and the chamber has a glass on the front of it. And as soon as you put glass in front of it, you have to put a lens in front of the glass to counteract the effect of the lens. So you have to have 2 lenses. So you end up with a primary lens, which is the biggest in the world. And again, you can see a person standing, but you saw the similar in the cartoon before, but there's a real person standing with the real lens. And we got another Guinness World Book of Records entry for that. It also moves incredibly fast. This is the telescope moving at 20% speed. The requirement for the telescope is to go from any point on the sky to any other point on the sky in less than 20 seconds, including 2 seconds of settling time. So, and it's completely silent, well, almost completely silent. It's just like Terminator, all you hear is zzz, and it's gone, like your electric car. It's the same technology. It's all brushless electromagnets that move this. So it's, I think if we didn't have Teslas and electric cars, we wouldn't be able to have this telescope because it's the same technology inside driving it. So we're going on the sky very soon. This is, we have a small camera with 9 CCDs on it, and we're going to put this on the sky in July. So it's a very exciting time for us. We're just getting ready. The mirror's coated. The big camera's arrived, but it needs a couple of months of testing and checking out on the summit before we put it on the telescope. So in the meantime, we have a small commissioning camera that allows us to check out all the optics. We have lots of software for that. This is just a picture. So we've already been using that telescope. I showed you it moving. So that's a telescope mount that has that one in that picture has the commissioning camera on the top of it. And on the back, it has the surrogate mirror that I showed you earlier. It doesn't have the real mirror. But it's the same weight and size, so we can do all the testing of moving it around the sky, making sure we can do our survey. And just to check, we had a couple of cameras mounted on the sides of that telescope, star trackers. So we can take star tracker images, so we know that when we ask to point somewhere, we can go back and look, yes, we actually pointed where we were supposed to. not the first few nights, but on the third night we had it all working and we actually got to where we were supposed to be. And so that's one of our quick looks. We process images from those cameras, and from the entire focal plane in about 6 seconds we can render the entire thing. Obviously you can't really look at that, it's too big, but we give you one image of the entire focal plane in about 6 seconds, so you can go, there's something there, it's not empty, which is the main point of it. In this case it's a star tracker, so it's kind of trivial, but it's the same system running alongside it. Prior to that, since about 2019, we've been running an auxiliary telescope, or what we call a calibration telescope. So this is a picture from outside, from the observatory just across. That's where our calibration telescope sits. So you mentioned earlier adaptive optics. We do not have adaptive optics. We have active optics. So the field of view is very, very large. In adaptive optics, you usually want to shine a laser, figure out what the distortion is, and then you want to counteract that distortion by manipulating your mirror. That works when you have a little field of view. When you have 9 square degrees, that's not going to work anymore. It's very, very difficult to figure out the distortion model and apply it quick enough to a huge mirror. What we do know about gravity, and every time we move this huge mirror, it sags. So our active optics counteract the gravity and reform the mirror to keep it in perfect harmony. So that's again one of the things that we've been testing with the surrogate, but one of the things that we actually have to really test with the real mirror, with the commissioning camera. We've now got a lookup table that says every time we move this thing, this is how much force I should apply to the mirror. And now we're going to put the commissioning camera on and see if that really works and tune that model up before we put the real camera on. And the first testing with the metal one is just, we didn't break anything. We can test the forces we were applying and make sure we're not going to apply too much force at any particular point. So if you can't do adaptive optics, you still need to calibrate out your atmosphere. We want a very accurate telescope. We want to be able to look at stars. We want to know what color they are. We want to know their photometry. And the atmospheres are really not helping us with that. It takes out a lot of photons from us and distorts things. So some clever astronomer said, well, if we had this other telescope nearby, and we just took spectra of really bright stars, that's like lasers. We know what the spectra of stars are. We know these bright objects. If we took enough images of them or enough spectra of them with a small telescope, we could figure out that telescope's characteristics. And then every night as we observe, we could just take spectra in the same field of view, and then later we could go, oh, this is what the atmosphere is over those stars, and then we can deconvolve that from the model mathematically. And just, the image doesn't matter, it looks fine to you, but we care about the number of photons that are collected in each star. So we can then use this information to help us unbias the atmosphere out of the calculations. So that's a mathematical way of doing it with spectra. There's a pure mathematical model that we also have called the forward global calibration model, where we model every star over 10 years. And of course you have 800 observations, I already said that, over 10 years of that star with different atmospheres. But you also have 800 observations of different stars at the same time with different atmospheres. So you can deconvolve the two of them by building a model for every star, for the atmosphere at any given time, and for every different star over 10 years. And you can work out what the actual photometry of each star is. So these are two new techniques. The forward global calibration model has been applied to the dark energy survey and does function, so we know that that works. The one with the telescope, that's completely new. We'll see how that works. So this is just a naming slide to help you with some names, because you asked me also earlier, LSST. We used to be called LSST, but we're not anymore. The facility, the observatory, was renamed the Vera C Rubin Observatory, after Vera C Rubin, who is one of the discoverers of dark matter in the universe. And this telescope itself is named the Simonyi Survey Telescope. So that's the big moving object that I showed you earlier. And we backronym LSST, which used to be the Large Synoptic Survey Telescope, to the Legacy Survey of Space and Time. That was quite clever, we thought. So we can keep that LSST thing, but it means something else now. And that's the actual survey which I spoke about before as well. Okay, so it's always interesting how much these things cost. You want to tot up how much your motorway costs versus a telescope. So building this thing, we got about 30 million in private funding, hence we have a Simonyi Survey Telescope. About 500 million from NSF, and the Department of Energy gave us the camera at a cost of about 200 million or something like that. So they built the camera as their contribution to the project. Operations starts in over 10 years of 365 million each from the two partners. So DOE and NSF do 50-50 on operations, more or less. NSF want to be 51% because they want to be in charge. So they're going a little bit ahead. It's a very international project. You have the TMA, the telescope mount assembly, so that big moving object, that was actually all built in Spain, in Asturias, by Asturfaito. The dome, of course, is Italian, because domes build domes, churches. Apparently Italians do that. All the domes in Chile are built by Italians, and they're all late. The French built some of the camera parts, the shutter for the camera, the filter system for the camera, all comes from France, and they also do some of the processing. In the UK, they're doing data processing for us in Edinburgh. The coating chamber that did that fantastic mirror coating on our mirror, that was all built in Germany and shipped. That's quite nice to have in the site. And then in Chile, of course, we're our host country. We get a lot of engineering and IT support directly from Chileans. So there's a company that built the whole control system. So there's a little picture here of the screens. Like you have a nice control system that shows you where the telescope is and lets you command things. Astronomers don't go up to that big telescope. They sit and type on the computer. That was all built by a Chilean company. And then, of course, lots of engineers on site. So it's a pretty international. It's nice. Okay, so another one of my photographs from up on top of the observatory in October last year. So it's pretty nice. It's a single exposure. It was 10 seconds. Not that bad, right? So this is another picture. Or if we're looking at that, you're all amateur astronomers, so it's 100 degrees across or something. It's big, it's wide, right? It's most of the Milky Way. And this is just a few arc minutes. It's a tiny patch of sky. And you mentioned I worked on Sloan, so this is a Sloan image from the Sloan Digitized Sky Survey. A few arc minutes. And just to give you context, that's 1/16 of 1 CCD on this camera. So you'd have to look at, what's it up here, 3,000 of these to make up one image coming off the Vera C Rubin Telescope. That's not the interesting thing, though. That's the Sloan image. This is the exact same patch of sky, but from hypersuprime cam. So we process hypersuprime cam with our pipelines already, and hypersuprime cam is a similar technology. It has the similar CCDs. It's not as big a field of view, and the telescope's not as nice, so it takes them hours to make this image. This is about 10 hours of exposures. But we'll do this in a few minutes with Vera C Rubin. And the thing for me, as data management, the problem, the nice thing about that, this is great, right? You can see there's a galaxy here, there's a galaxy there, there's 2 stars here. See, I can pick them out by eye. So software for processing this is easy. Just find most of these things, and there's a few complicated things. And now with Rubin, we've got this, where I've got galaxies that bleed into other galaxies. The stars are overshadowed by galaxies. What looks like a big patch of empty sky on the left corner, no, it's actually full of stars and galaxies. So everything is very crowded and blended. But that's what sensitivity gives us, right? That's the reasoning. And we'll get about 5 million of these images, right? Full-size images. That's 30 times 5 million of these, 60 million of this size. This is maybe a little bit technical, but again, since you're the Astronomy Club, I thought you might be a little bit interested in filter responses and what we get. The other people who don't care about astronomy, just you can look at your phone for a minute. So I said we have 6 filters. We look in 6 different color regimes across the spectrum, and our sensitivities are pretty good. So for our stacked images, we can get down as far as 25, 26. That image I showed you was actually 27, so we probably don't get quite as deep as the hypersupreme cam image. We will in the deep drilling fields. Again, just like to be technical, you have the black line up here is the atmospheric response. So we already don't get to see everything, right? Because the atmosphere takes some of the light out from us. And then the next dotted line is the filter response. So we have a piece of glass, which is the filter in a given color. That takes out another big bunch of light. So we reduce some more. And then the dark line is our final response. That includes the mirrors, the glass, and everything else in the system. So, even though we're super sensitive, we're still losing 40% of the light in the best bands. But this is what astronomy on the ground is like. So you asked, why would you go to space? I get number 1 in space. Okay, so and then the other thing that I've always found interesting, because my background is computer science, right? I think, and I've been drawn to these survey telescopes because I think they change the way people do astronomy significantly. And so it's one of my telescopes, Celestron 11, what do you say? Something very similar to what you have in Spain. My other telescope's in space. They let you touch the rockets. The guy was launched on a Soyuz. They walk up and go, they let me walk up and touch it. The other launch I went to was Ariane. It's like 2 kilometers. That's it. You can't go any closer. And then there's the Vera Rubin. So Gaia and Rubin are survey telescopes. There's no, I said to you before, no observing proposals. Astronomers don't come and say, I want to look at this thing. No, we just look at everything. All the data is there afterwards. And it's all homogeneously processed. So you start to do statistical astronomy. It's no longer an astronomer going, oh, I've made this interesting observation of this one object. I'll make one other one, okay. I have 2 objects. And now I'm going to make a theory about how the universe works from 2 observations. So now we're going to go, well, no. Here's 10 billion observations for you. Now make your theory work with 10 billion observations. And lots of theories break down once we do this. And lots of people don't like it. They say, oh no, we have to throw away all of those because those weren't good. And we go, no, they're just as good as the rest. Your theory must tell us why we made all of these observations, not the ones that you just liked. So it's a little bit different way of working. I like that. Okay, so this is, again, Vera C Rubin. This was one of the early tests in the camera. They did the classic pinhole, right? Just a pinhole in a piece of paper, held up a picture of Vera Rubin, and then took that picture with the full camera, and that's the full readout. Obviously not, it's scaled down, but you can see all of the CCDs, you can see all the gaps between them. That's what happens when you have big cameras like this. And that's what we process. So the 189 is a set of those 4K CCDs. In some of the bands, we will do 2 snaps of 15 seconds, although we're leaning towards it'll be just 1 30-second exposure for every band. Depends on light and seeing. There's still some discussion about whether 2 times 15 is better. I'm going to mention satellites. 2 times 15 is sometimes a little bit better for something like satellites. Okay, I see Clare is on. Good. So I'm going to. So then I mentioned we have alerts. We're going to process each one of those images in less than a minute. That's the target. The requirement is 2 minutes. But I start to fall behind because remember we're taking more than one image every minute. So if I spend longer than a minute processing it, I'm going to start falling behind a long way, trying to catch up on processing images and make those alerts. It's a big open source project. There's about 1 million lines of C++ and Python. It's all out there in GitHub. If you want to go play with some software or look at some real astronomy software or help us out with that, that would be fun. And as I said, you need a lot of TVs if you want to look at one of those images. So just to give you an idea how the survey works, I mentioned this already. We're scanning just basically across the sky. Every night we're just taking a picture, slight overlap, take a picture, move across the sky, try to avoid any clouds. There's an automated scheduling system. It has the weather built in. It's just telling the telescope, this is where you should go next, And it's remembering where it's been, because remember, we have to make these 800 observations. So if I miss this bit tonight because it's cloudy, I have to go back tomorrow night to get those images, just to get a homogeneous coverage of the sky. And yes, satellites. These are fun, not. I come from space, but my satellites are all out at L2, very, very far away. They don't interfere with anything around Earth. So this is from Tony Tyson, Mary Rolls on the project, just to give us an idea. This is lab data, so it's not on-sky data. It's from a laser in a lab simulating the magnitude of a specific satellite. This is also interesting if you're interested in, like, let's say raw images. You can see here, this is one CCD, and you can see each of the revs in the CCD, and you see how each one of them is slightly different because this is a very raw image. It's not being processed in the same way that we normally process images. But here you can see they put a streak across with a laser. It gives you an idea of how much of your image gets destroyed by a 7th magnitude satellite. And that's what people are aiming for. The Starlinks at the moment, you're seeing something like this. It's taking out most of the CCD when it crosses it. And Blue Walker, hopeless. If we get too many of those, we don't see anything anymore. And we have a huge field of view, so we're going to get a couple of these in every picture, basically. Whatever they are, especially around twilight and lower down. Oh, that got mixed up. Anyway, this was actually the continuation of the telescope story that we've moved into the era of surveys. This plot is interesting. It's from Hubble, and it's papers on the blue is the observers asking for their data, and on top, the big brown bit's just from the archives. So it's people going back, going, the data's already there. I'm going to write a paper on it. And so you can see back in the 90s when Hubble started and up to like 97, the observers were still writing more papers about the data they asked for. And after that, other people were just writing more papers about the data than the observers who actually asked for the data in the first place. And then when you had something like Gaia and Rubin, you don't even ask for the data anymore. You're just going to get the data from the archive. The paper's already from the archive. You never asked for it. You have to go in the archive and look for your data and make your request that way. So yeah, so this is the new science machine. It's just a big computer. And then, as I said, data access is with we have something called a science platform. We basically give you access to this data by logging into a portal. In there you can run some notebooks. The scientists can actually manipulate the data directly. The images are very large. We don't necessarily want people trying to download petabyte of data to their disk, wherever they want to be. Few of the bigger organizations, we might make some copies to them, some of the supercomputing centers, so people can work on them there locally, but more or less, we expect most people to work through our science platform to access the data. It's also kind of an interesting way of democratizing data. It means that everyone is the same. If you're here in UCC with a bad connection, actually it's a pretty good connection, you have about the same tools to work with as someone in Princeton. You'll be using exactly the same tools, you'll be logging into the same computer. This actually works better probably in places like Africa where they have very, very poor computing. If we can get them a good connection with Starlink, for example, they can manipulate the data and do the same sort of work as we do, which is quite nice. Okay, and then we're in citizen science. I thought we had with Zooniverse and with Claire. Are you?
I'm here. Can you hear me okay?
I hear you fine. Do you hear Claire?
Yeah.
So this is Clare Higgs. Can I put you up on the screen? Let me see, so they can see you. It's not behaving itself.
No worries. I can just be a voice if that's okay.
Okay,
I
go
don't
ahead.
mind.
Yeah, go ahead. That might be better.
Okay, awesome. So hi, I'm Clare Higgs. So I'm the astronomer on the Rubin Education and Public Outreach team, and I am currently sitting in very sunny Tucson. So it's nice to be able to join remotely to talk a little bit about citizen science with Rubin. So citizen science obviously is going to be a really interesting way to explore so many of these really interesting science areas that Will has been talking about, and tackle this enormous data set that we're going to get with LSST. And so really what we're trying to do is both support the scientists in our community in putting projects together, and we're trying to support volunteers who are really excited to use this data. So we're basically building a set of tools that allow connections from the Rubin Science Platform that Will was just mentioning, where all the data lives, straight to the Zooniverse. And I think, Will, if you go to the next slide, there might be some Zooniverse things. It's a really popular and well-known platform for all kinds of citizen science. So there's a sample here of astro projects that are currently on Zooniverse, but Zooniverse really hosts many areas of science and other research, including looking at handwriting and literature and things like that. But we're really hoping to empower our scientists to work with a global community to kind of tackle the amount of data that we're getting. And my role and position is to help both our scientists and the public. One of the numbers I kind of like to keep in mind is, so Will's mentioned the alerts we get every night. It's about 10 million alerts every night. If you wanted to look at 1% of those alerts by eye, that would take you about 27 hours. So, if we want to start kind of breaking down and having some visual inspection of this data flow, we need help to do it. So, sorry, Will, if you just step ahead again.
Yep. Yep.
Let me just see. Yeah, perfect. So if it sounds intriguing to you and you're excited to kind of get involved as maybe a participant or any part of this, we would love to kind of start a conversation. And so we are planning to have a series of talks, hopefully starting next month. I wish I could give you some exact dates, but we're not quite organized enough yet. And this series of talks will hopefully give an idea of what sort of science questions will be happening, what the data is going to look like, what to expect, and kind of get excited about looking at citizen science projects. We will both do these live, and we'll also have recordings, so time zone dependent. Hopefully it should be accessible to everyone. If this sounds of interest to you, I would say if you follow one of our social media, look on our website, which is there in the yellow box, or you can send me an email at cscience@lsc.org, and I'll definitely let you know the details of when it's all happening. Also on our website, I've linked a couple projects there, which are already existing projects that are on Zooniverse, that are doing some great work in their own right, but also they have different kind of flavors and aspects that are looking ahead to Rubin, and so can kind of start to get everyone excited for what's to come when Rubin comes online. So I'll leave it there, but I'll stay online if there's any questions after.
All right. Okay, so are there any questions for Claire, for citizen science? There's only a couple more slides anyway, and then we're going to go. Yes. Everything, there's loads of links and papers and documents and everything is in there, yeah. There were a couple of more sort of citizen science, but I think Claire mentioned most of these. I mentioned the UK do processing with us. They have a broker called Acer. So this was one of the things like supernova. They have a citizen science universe site that's looking for supernovae, and they want people to, we need eyes on them, as Claire said. So this is one of the sites set up for that. I mentioned Hypers Prime Cam. They have something looking for lenses. So this is one of the ways of looking for these kind of potentially dark matter things way out in the universe by the distortion around some other object. Planet 9, if we do our job properly, and I said to you, we get 90% of all of those smaller objects out near Jupiter. So I don't know if you know Planet 9, but Planet 9, people, there's a planet, there's another planet out there, there's a perturbation in these small objects, but actually it's a very small data set. It's exactly the kind of astronomy I mentioned before, where people, I've seen a few hundred things, there's a planet over there, but there's millions of things out there, you haven't seen the rest of them. Could be anything else. So we're going to provide an awful lot of data in the first year that will help to pin that down. Either we find Planet 9, or we find a lot of data that says they had an anomaly in their data set. Daily planet, minor planets, so again looking for asteroids, and Galaxy Zoo, obviously we're going to have billions of galaxies. Galaxy Zoo currently has 1 billion, we'll have 20 billion, so there's a few more years' work on Galaxy Zoo. And I think that's the end of the presentation. That's again more for information. There's some websites and other information sources, especially if you want to put people in press. There's some press kits and things coming out that are also interesting for people. And that's it. I'm going to stop. And if I can get Claire on the screen, I'll get Claire on the screen. Any questions? So, processing power. On the summit, just for like the observers at nighttime, I have 2,200 cores, if that means something to you. 100 cores, 2,200 cores. I have 20 nodes, 20 blades basically, each with a few hundred cores on them. So that allows you to process a couple of focal plane images in near real time. Well, as I said, we have 198 CCDs, so basically we process each CCD individually. So yeah, we can parallelize at least like a couple of hundred times, which is already good. But actually within that, we're pretty, we run a couple of threads, but not much. So basically we process each CCD as its own thing. And yeah, we might do a little bit more on it, but there's a terabyte, there's a few terabytes of SSD drives, actually almost a petabyte of SSD drives, and then I have another 35 petabytes of hard disk sitting under that. And in Slack, where the data ends up in the final, there's also a tape robot that's backing it all up to tape. And then we send it to France as well, and they keep a copy. So we have 3 copies around the place. There was a question at the top as well.
I'm just wondering, is there any other questions for Claire as she's online, specifically relating to citizen science?
I have the same question for Claire. What would we have to have in the line of computer power to partake in any of our experiments?
So Claire, I don't know if you heard that or not, but he's asking what kind of computer power you'd need for citizen science participation.
So, thank you. Thanks for repeating it. I can barely hear. You shouldn't need any computing power to kind of access the Zooniverse side. Yeah, most of their stuff not quite optimized for doing kind of on a mobile, but doing it on a desktop or on your laptop. It's very, very accessible. So yes, our pipeline hopefully reduces the resource burden on our project scientist leads, and the Zooniverse is a platform that is designed to be globally accessible and have minimal bandwidth.
We got you on the big screen.
I got you on the big
eventually
screen, Claire. Now you're very large in the
okay.
auditorium.
Great. Anything else, Claire? Now that we have her on screen? Yeah.
Maybe I missed it, but I'm sorry. When you've got these very long exposures from data sets, how do some look at some atmospheric variability, you know that?
Yes.
Did you say already how you got that or?
Yes, so there's two techniques for the atmosphere. So one is that we will take, with the calibration telescope, we take spectra at the same time that we're observing. And then when we... Yes, so then we use the standard candles from the spectra, they're just bright stars. And if we can work out that distortion, that gives it. But we also do the forward global calibration model where we model the atmosphere and all the stars in the big field of view over many years. And then we make a model for the atmosphere as well over time, as well as for every star. And so we should be able to deconvolve the two with like a few years data. You have enough statistical weight behind the observations at different times that you can work it out. So we have two techniques for basically doing it.
And anything else for Claire? Now that we can both see and hear her. No? Okay, Claire, thanks a million. That was amazing. And I'm sure there will certainly be some interest in the citizen science element of it. We have one or two club members that are very involved in citizen science and have actually been mentioned in papers. So, yeah, I'm sure there'll be people very interested. Yeah.
That's fantastic. Thanks for letting me chime in. And yes, please do feel free to reach out if you have any thoughts or anything you're particularly interested in. We're really excited to start getting our volunteer community growing and ready for Rubin.
That's all.
Thanks so much.
Thank you for joining us, Claire. Thank you.
All right.
Okay, coming back to William's side of it, can I kick off one quick question, Pat?
Yeah, what would you say is the most surprising thing you've discovered so far, or is there one thing that stands out?
So not me, but like from Gaia, I don't know if you followed the news most recently, but they just found a huge black hole in our galaxy, another one. Mm-hmm. So they're starting to find all these black holes because we now have a little bit like the dark energy. Now we have all of this picture of the motions of a billion stars, which is, a percentage of our galaxy finally. You're starting to see interesting effects from that, and I think these black hole discoveries are the most interesting. That like black holes are far more frequent than we thought. We're beginning to see this anyway because of LIGO going, oh, well, these black hole mergers, and you're starting to see them in the gravity waves. And there's also looked like, oh, there's actually more of those than we expected. So clearly there are more black holes, but now we're starting to find them with something like Gaia. And all of that's going to come out. But like for Rubin, it's impossible to say. It's going to be very surprising for sure. There's going to be loads of things we didn't think of. Right. And then the other thing was Amina Helmi's galaxy mergers. I mean, this is again a theory, but actually seeing the data that says, yeah, no, it happened. That for me is the best.
Yeah. And as Professor Brian Cox told us last week, I mean, the information that we're going to learn from studying black holes is really going to change our understanding of the universe pretty significantly. We did an amazing presentation on it. One question I have for you is on a mirror. So you have one mirror, I assume.
Yes.
Yes. Because
we have two actually.
That's what I was wondering.
So yeah, maybe I could explain that very easily.
At times one needs to get swapped out and recoated.
Oh no, sorry, so the telescope's a 3-mirror anastigmat, if you understand what that means.
No.
So it has 3 surfaces that reflect light.
Okay.
There's the primary mirror, that's the 8.4 meter mirror, and light comes in and hits the primary mirror, and that's a concave mirror that reflects light back up to the secondary mirror. So we have a secondary mirror, it's 3.4 meters, I can't remember. Secondary mirror, that's a convex mirror. And so when you do this, you get rid of some of the astigmatism from the observation. And that reflects back to the tertiary mirror. And the really interesting thing about Rubin is that primary and tertiary mirrors are one piece of glass. So I don't know if you noticed the funny shape of that mirror when you had this blue thing, there's 2 concave surfaces. So it's 2 separate mirrors, or 2 optical surfaces with 2 different purposes. That's the third mirror that reflects it back into the camera, and the camera's sitting up in the top of the telescope. And so, no, there's no spares for those. That's why we have the coating chamber in the observatory. We can take the mirror off, put it in the big elevator, we bring it down to the third floor, we stick it in the coating chamber, and we recoat it.
And so the whole telescope is going to be offline during that period, obviously.
Yes.
And what kind of a time is that going to be?
So the initial design said it would happen every 2 years. Gemini's works for 5 years, so we could be 5 years. Could be 2 years, could be 5 years.
Right.
We won't know until we actually start using it.
Okay, but the recoating process?
Oh, the recoating process, so that was the little video, we could play it if you wanted. That's 4 hours of actual coating, but the prep work is about a week to get it into this. It has to be cleaned, moved carefully, and put in place.
So the whole telescope will be offline,
Offline
for
for
2 weeks?
Yeah, 2 weeks, yeah.
Okay.
Yeah.
So does the secondary have a hole in it?
Yes,
Yeah.
and the camera sticks right through the middle of the secondary. Yeah.
Not unlike a Schmidt Casimir.
Yes, yeah.
Yeah.
It's probably quite a stupid question, but it's 2 questions.
Sure.
The first part is, what is Rubin's range versus the JW telescope? And that's A of part 1. And B is, if it's less, then what functions is it doing that JW is not doing? So that's the first question. The second question is, we had a lecture about simulation of the universe and so on at one stage. And I know it's only a simulation, but vis-a-vis the edge of the universe, what amount of fraction of that distance does Rubin actually go as far as?
Those are tough questions. So James Webb is a completely different design. It's a spectrograph, and so we're working in optical wavelengths. So they don't take the same type of images even. It's a very, very, very narrow field of view. James Webb wants to look at the atmosphere of a planet through with the light coming through the planet's atmosphere from the star behind it. So you're looking at these very tiny things very, very far away, whereas we're looking at like this much of the sky every time we take a photograph. So it's the scales are completely different. And you're asking the 40 billion galaxies what the maximum redshift. I don't know whether is Clare still on. She's left. Oh, I'm abandoned. I don't know what I don't know the furthest galaxies.
Computer's range. Like, it's only a simulation. You don't know what you're doing.
Well, yeah, but you asked me how we have an idea how old galaxies are that we look at at great distances. By basically basically the idea is redshift. So they look redder the further away they are. So when we start making these observations, we'll see some very, very red galaxies, the very faint ones that are very distant from us. And then your question is difficult because the distance ladder for figuring out how far away that really is one of those things that's entangled up with like Gaia data, where we finally begin to figure out the distance of some of our local stars, which were always very badly measured because we did parallaxes from Earth instead of from space. Now we start to have some good distances for those, and that's changed a lot of what they call the distance ladder. So they started using, the quasars are used for that, and aurora Lyrae, these particular types of stars that people said, well, if we knew the distance to this star, those type of stars are always like this, so if it's fainter and over there, we can tell from the faintness how far away it is. So those things are all tied up together. So I don't have a good answer for you like Kang that says, we're seeing the first giga-year of the universe, but it's something like this. It's the edge of the optical. It's about as far back as you can see.
Thank you.
Over here, John?
Just in regard to satellites, is there anything happening nationally or internationally to try to control the amount of satellites going on different things?
So Tony Tyson, who's our chief scientist, he actually has meetings with people like Elon Musk. They've in general agreed to try and keep their satellites at around about 7th magnitude. So I showed you a picture of one of the Starlinks, which is not great. They were convinced that this was not great. The newer generation of Starlinks, they've started painting them with a less reflective, like black paint and things like that. So they've consciously started trying to change them. We're not going to get rid of them. Yeah. So yes, there's several side astronomy meetings at many of the big gatherings like AAS, where maybe Musk doesn't show up, but people from Starlink and from the other satellite companies are showing up and having conversations with us, because they don't want to be the super bad guys. We started a lot of like, well, you're basically ruining the sky for everybody forever. And they go, well, bringing the internet to everyone in the world. You can't argue with that. It's kind of true. So somewhere there's a trade-off. So they go, well, we know they're launching them, so at least can you try to make them a little bit less bright? There's a lot of collaboration, I think, about trying to do that. But the problem is, okay, we're talking to Bezos and Musk. They're Americans. That's fine. The Chinese are going to launch like thousands of these things in the next year. They already have a plan. They want to, they're going, Starlink's great. We need a Chinese Starlink. So they're going to launch another 40,000 satellites. And they don't necessarily talk to us about it. So
that's why I just asked the question. I was already happening on the international scale, like say at United Nations level.
I don't know about the United Nations. Okay. All I know is that like every country that can launch a satellite says they want to now have their own GPS. They want their own communication satellites. And they're not talking about one anymore. They used to launch one. Yeah. Now they want to launch 40,000 because Starlink has proved that this works really well. Yeah. The Ukraine war has convinced everyone that you need military satellites, basically.
Yeah, on that slide you had Blue Wave, was it?
Yes, the Blue Walker.
Blue Walker, was it?
I'm
not familiar with them. Who were they?
They're going to be Blue something. That's Bezos, isn't it?
Is it?
Blue, forget.
Are you very familiar with them?
Is there much agreement about collecting debris in space?
Everyone thinks that's a great idea, yeah, but nobody's doing it. So ESA actually have, I think, 2 experimental missions and Japan have one. So there's a lot of experimental, research missions about how would you gather some of that debris. Also, there's a couple of missions for how can you decommission satellites, because the biggest problem is satellites that get decommissioned, they run out of fuel, you can't move them anymore, and then they're just sitting there until something hits them, and then they break up, and then there's lots of debris from that, and then that starts to make more debris because it runs into more satellites. So there's a couple of things like these, one of them is to watch exactly what you think, go up with a big net, grab the thing, drag it down into the atmosphere so it burns up before it breaks up. So there's lots of these, but they're all in study phase. Nobody's launching them. And then you think about that's one satellite to go and get one satellite, and there's thousands of those things out there. So
more to find out that information.
So the international agreement with launching says that you are supposed to keep enough fuel to deorbit your satellite safely before its end of life. So we do that at the European Space Agency. All those satellites, we keep a fuel reserve to get it out of orbit. But not everybody, that's the international agreement, doesn't mean it always happens.
So the trick then is to blow one up and let the debris take after the others.
Yeah, the problem is to take them all out. It's a little bit indiscriminate. Yeah.
Sway them out at a time.
Yes.
We get a light show and
you get a new belt around Earth.
Any other questions?
Exhausted everyone.
Exhausted
they want to go to the pub.
I wish. Right, we'll go back to here, hopefully. Okay, so I just want to thank William for that absolutely amazing lecture. We all look forward to seeing the telescope come online and to see the results that it's inevitably going to produce. As you say, it's going to change lots and lots of things because you're going to provide just so much data out there. So, on behalf of Cork Astronomy Club, a very small token of our appreciation of yourself and Grandpa for coming along tonight.
Oh yes, very nice, Celeste.
Celeste. Well, we thought it was apt.
It's very apt.
Yeah,
Thank
very
you.
apt.
Thank you.
Not at all. Not at all. Thanks.
Right.
Just one or two reminders, and we can